Hey everyone, so this is an example of a limiting reactant problem, and as you can see I have a reaction written out for you. So you have ammonia plus oxygen plus nitric oxide plus water. Those are awful lines. Remember, before you'd even attempt to do a limiting reactant problem, make sure it's balanced. I decided to balance it before just to expedite the process, but you never know, it could be unbalanced and your answers would be wrong potentially. So make sure you balance it beforehand. Now, a limiting reactant problem requires you to essentially, have ingredients. You have reactants. I'm giving you a mixture of reactants, and you need to figure out which one is consumed first. So in general, you're going to want to arbitrarily pick a product. So I'm going to pick nitric oxide as what I'm going to form, so to speak. I'm going to compare the answers in the end of how much NO is going to be formed with either 2 grams of ammonia or 4 grams of oxygen. Now, requires a few dimensional analysis steps. So if that's a little tricky for you, then what you can do is start by making what I call a roadmap first. So let's say we're starting with grams of ammonia, and like I said, I want to figure out how much NO in grams it will form, okay, if we add any amount of oxygen. So you start with grams of ammonia. Well, you need to go to moles of ammonia because that is really the only way you can get from one molecule to another, because you can use mole ratios. If you're at moles of ammonia, you can then go to moles of NO. And then if I want grams, you do molar mass again to get grams of NO. So that's a typical roadmap, okay? Each arrow represents essentially a fraction, a dimensional analysis type problem. Now, limiting reactants also limiting reactant problems also are paired with how much is in excess of the other reactant. So we don't know which one's a limiting reactant, therefore we don't know who's in excess, but we can answer it after. So let's get going. Let's start with the first one, ammonia, right here. I want to know how much in grams it can make of NO. So we start with 2.00 grams of ammonia. Using our roadmap, we're going to do a little dimensional analysis. So grams of ammonia is on the top for this first problem, fraction, so to speak. So we're going to put it in the bottom of the second. And because it's molar mass that we're trying to get to, we're going to put moles on the top. So what is the molar mass of ammonia? Well, it's 17, defined in 1 mole, okay? Our next part of the roadmap, we need to go to moles of NO. So moles of NH3 goes on the bottom, moles of NO goes on top. So how do you actually figure out the mole ratio? Well, this is when you need a balanced reaction. So we had 4 ammonias to 4 nitric oxides. So in general, or specifically, this is going to be 4 to 4. Last step, because of our roadmap, tells us we need to go to grams. So moles go on the bottom because you're canceling that out. 2 grams on the top. What is the molar mass of NO? 30. Add up nitrogen and oxygen. I ended up getting, for this first round, 3.53 grams of NO. That's how much NO was made if you start with 2 grams of ammonia and you have any amount of oxygen. Okay, now let's do this whole thing again, but with 4 grams of oxygen, okay? 4 grams of oxygen. First step. It's the same steps as before, we're just doing oxygen. So you're going to do grams of oxygen on the bottom, 2 moles of oxygen. Molar mass of O2 is 32, defined in 1 mole. Now we're going from moles of oxygen to moles of NO. Balanced reaction tells us that there are 5 moles of oxygen to 4 moles of NO. So we have a 5 to 4 ratio now. Last step, moles of NO. Whoa. That was fun. moles of NO to grams of NO. It's the same step as before. We have 1 to 30. You'll notice that I'm doing my units first and then I fill in the number. That's just what I do because I like to show people that if you do it that way, you're most likely not going to flip the fraction. And many times people flip the fraction if they're doing the entire number and the unit together. The answer I got here was 3 grams of NO. Now you need to actually analyze your answers. So the point of a limiting reactant problem is you say, well, if you had these two scenarios, which one made less of the NO? That would be oxygen, because it made 3 grams instead of 3.53. So your limiting reactant is what? It's O2, okay? That means NH3 is your excess. So we've answered part 1. The limiting reactant is oxygen. How much is in excess? Well, now we know that NH3 is the excess. So we need to figure out how many grams of NH3 would be consumed. So with that in mind, we are going to start again with 4 grams of oxygen because we need to go 2 grams of NH3. So same step where we have grams of O2 and then moles of O2. So we have 1 to 32. And then we have this step, we're going from moles of O2 to moles of NH3, right? And if you look above, we have how many moles of NH3? We have 4 to 5 of oxygen. So we have a 5 to 4 ratio again. Last step, we need to know grams. So we're going to go moles of NH3, grams of NH3. And we have 1 to 17. I got 1.70 grams of NH3. And this is what is consumed. So you'll notice it's less than what it started with, which was 2. So the excess, that is not an E, but it's good enough, is 2.00 grams minus what was consumed. So you're left with 0.30 grams of NH3. That is the answer to the second question, right? So it's kind of, you have to interpret the question as well and interpret what you start with and what you're ending with, okay? So hopefully this gives you a little bit of an idea of how to attempt these limiting reactant problems because you'll see it, versions of this time and time again.